Short address/parameter attack. This attack is not performed on Solidity contracts themselves, but on third-party applications that may interact with them. This section is added for completeness and to give the reader an awareness of how parameters can be manipulated in contracts. For further reading, see the ERC20 short address attack explained. The vulnerability. When passing parameters to a smart contract, the parameters are encoded according to the ABI specification. It is possible to send encoded parameters that are shorter than the expected parameter length. For example, sending an address that is only 38 hex characters instead of the standard 40 hex characters. In such a scenario, the EVM will add zeros to the end of the encoded parameters to make up the expected length. This becomes an issue when third-party applications do not validate inputs. The clearest example is an exchange that doesn't verify the address of an ERC20 token when a user requests a withdrawal. This example is covered in more detail in Peter Vassinis's post, The ERC20 Short Address Attack Explained. Consider the standard ERC20 transfer function interface, noting the order of the parameters. Function transfer with two parameters, address 2 and uint tokens. Public returns, bool, success. Now consider an exchange holding a large amount of a token, let's say REP, and a user who wishes to withdraw their share of 100 tokens. The user would submit their address 0xDEA ... and the number of tokens, 100. The exchange would encode these parameters in the order specified by the transfer function, that is, address, then tokens. The encoded result would be A9059 ... ending with 5 zeros. The first 4 bytes, A9059CBB, are the transfer function signature/selector. The next 32 bytes are the address, and the final 32 bytes represent the uint256 number of tokens. Notice that the hex 56BC ... ending in 5 zeros at the end corresponds to 100 tokens with 18 decimal places as specified by the REP token contract. Let us now look at what would happen if one were to send an address that was missing 1 byte, in other words, 2 hex digits. Specifically, let's say an attacker sends 0xDEA ... as an address, missing the last 2 digits, and the same 100 tokens to withdraw. If the exchange does not validate this input, it will get encoded as A9059 ... ending in 7 zeros. The difference is subtle. Note that 00 has been added to the end of the encoding to make up for the short address that was sent. When this gets sent to the smart contract, the address parameters will be read as 0xDEA ... ending in 2 zeros, and the value will be read as 56BC ... ending in 7 zeros. Notice the 2 extra zeros. This value is now 25600 tokens. The value has been multiplied by 256. In this example, if the exchange held this many tokens, the user would withdraw 25600 tokens to the modified address, while the exchange thinks the user is only withdrawing 100. Obviously, the attacker won't possess the modified address in this example, but if the attacker were to generate any address that ended in zeros, which can be easily brute-forced, and used this generated address, they could steal tokens from the unsuspecting exchange. Preventative techniques. All input parameters in external applications should be validated before sending them to the blockchain. It should also be noted that parameter ordering plays an important role here, as padding only occurred at the end. Careful ordering of parameters in the smart contract can mitigate some forms of this attack. Unchecked call return values. There are a number of ways of performing external calls in Solidity. Sending Ether to external accounts is commonly performed via the transfer method. However, the send function can also be used, and for more versatile external calls, the call opcode can be directly employed in Solidity. The call and send functions return a boolean indicating whether the call succeeded or failed. Thus, these functions have a simple caveat in that the transaction that executes these functions will not revert if the external call fails. Rather, the functions will simply return false. A common error is that the developer expects a revert to occur if the external call fails and does not check the return value. For further reading, see number 4 on the DASP Top 10 of 2018 and Scanning Live Ethereum Contracts for the Unchecked Send bug. The vulnerability. Consider the following example. Contract lotto, open brace, boolean public paid out equals false, address public winner, uint public win amount, function send to winner with no parameter, public, open brace, require, negation of paid out, winner.send of win amounts, paid out equals true, close brace, function withdraw leftover with no parameter, public, open brace, require, paid out, message.sender.send of this.balance, close brace, close brace. This represents a lotto-like contract where a winner receives win amount of Ether, which typically leaves a little left over for anyone to withdraw. The vulnerability exists on line 11, where a send is used without checking the response. In this trivial example, a winner whose transaction fails either by running out of gas or by being a contract that intentionally throws in the fallback function allows paid out to be set to true regardless of whether Ether was sent or not. In this case, anyone can withdraw a winner's winnings via the withdraw leftover function. Preventative techniques. Whenever possible, use the transfer function rather than send, as transfer will revert if the external transaction reverts. If send is required, always check the return value. A more robust recommendation is to adopt a withdrawal pattern. In this solution, each user must call an isolated withdraw function that handles the sending of Ether out of the contract and deals with the consequences of failed send transactions. The idea is to logically isolate the external send functionality from the rest of the code base and place the burden of a potentially failed transaction on the end user calling the withdraw function. Real-world example, Etherpot and King of the Ether. Etherpot was a smart contract lottery not too dissimilar to the example contract mentioned earlier. The downfall of this contract was primarily due to incorrect use of block hashes. Only the last 256 block hashes are usable. See Akil Fernandez's post about how Etherpot failed to take account of this correctly. However, this contract also suffered from an unchecked call value. Consider the function cache in lotto.sol. Notice that on line 21, the send function's return value is not checked. And the following line then sets a boolean indicating that the winner has been sent their funds. This bug can allow a state where the winner does not receive their Ether, but the state of the contract can indicate that the winner has already been paid. A more serious version of this bug occurs in the King of the Ether. An excellent postmortem of this contract has been written that details how an unchecked failed send could be used to attack the contract.